Hi guys, in this video we'll begin looking at the chemistry of alcohols and ethers. We have this handout here with a warm-up page which shows the drug clindamycin, and it asks a question here for you to consider. Now if you had me before, such as for Organic 1, you know a number of my handouts include warm-up pages that give us a glimpse of the chemistry we're going to be doing. Often some of the questions are kind of advanced, but the idea is to sort of see what type of questions you can hopefully answer after we cover some of the material. I also tend to give you some interesting chemistry or applications. My background being in drug discovery, I often include drugs as examples to illustrate the chemistry. In addition to this handout, we also have the alcohol ether epoxide topic summary page. And we'll begin here with the chemistry of alcohols, and we'll sort of work our way around, and we'll begin with the substitution reactions of alcohols and then move on to elimination, etc. But this is an overall summary page. One thing I think it's important for me as an instructor, but also for you as the student looking to learn the material, is to try to be very organized. And my handouts, I try to give you some organization and that we can refer back to and to sort of see what we're doing, sort of set the stage. Okay. Now I will also note that this chemistry early on is going to be a good amount of review from Organic 1. You should have seen substitution reactions of alcohols in Organic 1 when you were doing SN2 and SN1 reactions. Also elimination and O-alkylation. So a little bit of review, but it's very good because substitution elimination reactions are very important. And please remember that the final exam in Organic 2 covers both Organic 1 and 2. And so I've always thought it's very worthwhile to do some review of these important reactions as we look closer at the chemistry of alcohols and ethers. Okay. The next page is also a little bit of warm-up. This is actually a mechanism question. It's actually a bit challenging. It's very relevant though. Morphine, a long time ago, was found to undergo a reaction with hydrochloric acid and was converted to a compound known as apomorphine. But what's the mechanism for this reaction? And if you look at it, it's largely alcohol and or ether chemistry. Again, a bit challenging here, but it's something to think about. Hopefully as we move ahead and you review your chemistry and learn more of the chemistry, this will become more doable. Now the reaction below is a synthesis reaction, predict the product, and it's actually much more kind of straightforward. I would hope that you would be able to do this in a reasonable fashion here without having to need a lot of review. A reaction of morphine. Which is a very interesting molecule and historically very important and remains important today in treating severe pain, management of pain. Okay. Next we have nomenclature. The nomenclature, as I've mentioned in other places, is covered by video, but it's covered separately. Those are separate videos that you'll find on the YouTube page. But the handout is included here, which you'll want to have when watching that video. Nomenclature of alcohols and ethers. And so we can move ahead to right here. Here's our heading. Okay. I'm big on headings. What are we doing? Covering the chemistry of alcohols. We're going to be looking at reactions and synthesis. Where in your textbook? In the third edition, it's moved to chapter 12. Okay. And we'll begin with Roman numeral 1 under this heading, Substitution Reactions. I told you that right here. Okay. Substitution, we're going to replace or substitute the hydroxyl group with some type of nucleophile. All right, I'll give you some notes here. Typically things that are written, very important to know. What type of mechanisms can we do here? All right. Mention here, the OH group is a poor leaving group for rate determining steps. Quick question, in which mechanism does the leaving group leave in the rate determining step? SN1 or SN2? Those are the two substitution mechanisms we'll be using here early on. Okay, think about that. OH is a poor leaving group. You have to make it a better leaving group. The most common way is to protonate it, okay, using strong acid. Okay, H+. Strong acid. And the leaving group in this case actually is not the hydroxyl group, but the protonated oxygen, and it leaves as water. Okay, underneath Roman numeral 1A, reaction with HX. All right, if you react an alcohol with HX, well, what is X? It's generic typically for halogen, most common HCl, HBr, HI. Okay, not HF typically. This reaction gives what? Alkyl halides. Here's an example here. Take this alcohol, which by the way, if you're watching Nomenclature, this is 1-propanol. React with HBr, we get the alkyl bromide specifically. Alkyl halide. All right. If we completely balance this, what else is formed? All right. Now in any of my videos, you can always quickly pause it if you want to try to answer questions yourself. And I would recommend doing that, because if you do the thinking yourself, you're going to learn things better. All right. Should be pretty straightforward. It's plus water, right? Which is actually the leaving group. Now it's completely balanced. We can show mechanism here. Importantly, things to remember, the nucleophilic strength of your halides. Iodide is stronger than bromide. All right, that's bromide stronger than chloride. Chloride is much stronger than fluoride. Fluoride typically is a very weak nucleophile and does not do substitution reactions. If you had me for Organic 1, we mentioned that many times. Now also, when things are typed, sometimes we don't show full structure. In the Organic 1, I ask you anytime you show a charged atom, you want to show complete structure. So you want to have 4 lone pairs on your halide, and you want to have your charge, and you want to circle it. All right. Again, when you're typing, it's much more difficult to show things like this. Okay, let's show mechanism here. We have predict the product. All right, you need to be able to predict that product there, because reaction of alcohols with HX typically give alkyl halides. There you go. But we also need to know the mechanism. First step here, we have H+, and we have Br-. We can show that ionized. That's okay to start. And we want to show the lone pair reacting with the H+, and we can protonate our oxygen, standard acid-base reaction. All right, that would be step 1. Now it is an acid-base reaction, but the equilibrium is not good. Okay, this is reversible. Any acid-base reaction, and actually reversible is favored. All right. You can look at pKa's. I'm not going to do that here, I don't think. It's not a complete reaction, but we can protonate some of that alcohol. All right. At that point, then, now we have a choice. Is the leaving group going to just leave, ionize away and make carbocation, or, which would be SN1 chemistry, or will the nucleophile have to come in here and kick off the leaving group? Well, this is a primary carbon. In Organic 1, we hopefully learn we typically never want to make carbocation on a primary carbon. Okay? So, which mechanism is this? By the way, we didn't mention this, but this reaction to give alkyl halides here can either be SN1 or SN2. As we learned in Organic 1, hopefully if it's primary, typically if your leaving group is on a primary carbon, typically always going to be SN2. No carbocation formed here. But if your leaving group is on a tertiary carbon, it's always going to be SN1 because you don't do backside attack. You don't do SN2 on a tertiary carbon. All right, this is easy. Primary, this is going to be SN2. Nucleophile, just come in here and kick that off. These electrons move in here and attack carbon. These electrons excuse me. These electrons move on to oxygen. Anytime you have a mechanism arrow, you begin by saying these electrons. That will help you get your mechanism arrows correct. All right, if you use mechanism arrows incorrectly, you're going to lose points on mechanisms. This is a concerted backside attack. This gives product plus H2O. All right, oxygen now has its lone pair back. Where does the lone pair come from? These two electrons were a bonding pair. They break away from that carbon and move on to the oxygen to become the second lone pair. All right, SN2. Hopefully looks very familiar. Now, SN2 involves backside attack with inversion. If we had stereochemistry here, we would need to account for that, but there is no stereochemistry in this example. We have kinetics to consider, rate laws, so everything that goes along with your understanding and knowledge of SN2 reactions. It's a two-step mechanism. Okay. This is a step here. This is an intermediate. Students say, "Well, I thought SN2 didn't have an intermediate." Well, it doesn't. There's your SN2. There's no intermediate in going from here to here. That doesn't mean we can't have a step like an activation step. This overall mechanism has two elementary steps. One is an activation step, and the next step is an SN2 substitution. The entire thing is not All right, so if you should be able to plot this on a reaction coordinate diagram. Okay, think about that, try it, ask questions, etc. Let's try the next one. To react this alcohol, by the way, that up there is a primary alcohol, okay? In the nomenclature, we go over that, pretty straightforward. The OH is on a primary carbon. Down here we have a tertiary alcohol. Tertiary alcohols react with HCl. We get this alkyl chloride. But what stereochemistry do we expect? Because this is a chiral carbon. By the way, is it R or S? Okay, you can pause and practice. All right. I want to do it real quick. The oxygen would be 1. Phenyl, that's a benzene ring, okay? It's a carbon with 3 bonds to carbon, that would be 2. Ethyl would be 3. The low priority group is in the front. This looks like clockwise, but the low priority group is in the front. Counterclockwise, that looks like S, yeah? I'm dying to put that in a Fischer projection. Alright, remember Fischer projections? I'm going to do that. Let's put the OH here. Let's put the methyl on the left, the phenyl on the right. Okay. And have the ethyl going back. 1, 2, 3. Yes. Clockwise, yeah. The methyl's coming forward, so we reverse that. Okay, just like I was seeing. Yeah, it's S. Okay. What kind of chemistry can we do with HCl? Well, the only thing I can see is we can protonate the OH. Okay. OH groups can be protonated. Have that there. Tertiary carbon, we have a Cl minus hanging around. But we don't do SN2 on a tertiary carbon. Remember? Alright, tertiary always SN1. Water just needs to leave. That's going to happen pretty easily. Loss of water is going to give us a carbocation with a phenyl and a methyl. Alright. But at this point the stereochemistry is gone. Because this is trigonal planar. Alright. Doesn't matter how I show the 3 groups on that carbon. Trigonal planar. I can flip it over if you wanted. I can rotate it. It's all the same. Now the chloride attacks. And now we get that product. And what type of stereochemistry do we expect? We have a carbon with a phenyl, a methyl, and a chlorine. But we expect that to be, it is a chiral carbon, racemic. Okay? Let's talk about this just for review. That chlorine, that's a planar, okay? That carbocation's planar. The chlorine comes from either the front or the back. If it comes in from the front, okay, I'll keep the methyl in the plane. If it comes in from the front, the chlorine's going to be forward, and it'll push the phenyl back. But if the chlorine comes in from the back, it will be back, and it will push the phenyl, the benzene ring, forward. Okay? And you will get both of these in a 50-50 mix. And that's called a racemic mixture. Okay? Racemic. We can just indicate that generically, but that's what that means, right? One is R and one is S. You can do those on your own. That's the outcome. Now this is SN1. A two-step mechanism. That is leaving group leaving and then nucleophile attacking. All right. Typically, this is your rate determining step. Leaving group leaving, back by the way up here, this was your rate determining step. But we did have an activation step. So there's 3 elementary steps overall. Down here we have 2 intermediates. Up above we only had 1 intermediate. Again, hopefully this is review. Okay, there's a couple here for you to work on your own. Note, what do you need to do this chemistry? You need a strong acid, H+, and you need halide. Those two can come together, or I should say, HX supplies both of those. HBr supplied both of those. That doesn't mean these cannot be supplied in some other way. Okay, here, sulfuric acid can supply the H+, and potassium iodide can supply the I-. All right? Because maybe you don't have any HI in the stockroom, but maybe you do have these two. All right? Then the reaction below. That's interesting. The chlorine is not on the same carbon as the OH. All right. Next topic here. Note we're still under substitution reactions, but there can be many miscellaneous things under that topic. One is the Lucas test. Now the Lucas test can be used to tell us what type of alcohol do we have. Do we have a primary, secondary, or tertiary alcohol? Okay, is maybe you have an unknown. All right, my water bottle here. But what if it was a bottle of an unknown liquid in the lab? Maybe we see it's an alcohol because of IR or something, but is it primary, secondary, or tertiary? I don't know. Well, we can do a Lucas test. And in this test, we react our alcohol with a combination of ACl and zinc chloride. And we see how long it takes for a separate layer to form. Now, this reaction, this test only works with water-soluble alcohols. And when you add the reagent, which is called the Lucas reagent, and you mix it up, you're looking to see how long it takes to go from one layer, that is the alcohol mixed with water and all soluble, one layer, how long does it take to become two layers? Now it becomes two layers once the alcohol is converted to the alkyl chloride. Because with the OH group gone, this no longer has hydrogen bonding, and the idea is that this is then going to be no longer soluble in water. All right. Now, if your starting alcohol is not soluble in water, this is not going to be a viable test because there will be no change. So that's why it only works if the starting alcohol is soluble in water. That actually limits the test a good bit. But it's still historically an important test. And it's also important to understand the mechanism and why the variation in time. First off, this is an SN1 mechanism. Okay? Now the zinc chloride is a Lewis acid. And it's a little bit complex, but what can be happening here is the OH group could actually, in addition to attacking H+, it could attack the zinc Cl+. Okay? And we can get if we show this zinc covalent, okay, we can get a positive oxygen like this. All right. Importantly, though, that's a Lewis acid. What's the definition of a Lewis acid? All right. If you recall that definition or look it up, then you will see that indeed that's what's going on here. From that point, this can ionize and we can get our carbocation, then the Cl minus, okay. I started by showing this ionized here, but then the Cl minus can attack. It's carbocation chemistry, it's SN1, we get the attack and get an alkyl halide. But if it's tertiary, this is going to be very fast. Okay? Again, this is typically your rate determining step. If it's secondary, this is going to be slower and it's going to take a few minutes, like 5 to 10 minutes. If it's primary, well, you're never going to form a primary carbocation, so you might as well just keep waiting. You're not going to get the alkyl chloride, and it's never going to form two layers. Okay? And so the difference in how long it takes to see two layers can tell you if you have tertiary, secondary, primary alcohol. That's the Lucas test. Sometimes we actually do a Lucas type reaction in Organic 2. I'm not sure if we're doing that this semester or not. I think it is in the lab manual though. Okay, B. Well, what was A? Reaction with HX. We're still doing substitution reactions. Let's look at tosylates. We should have saw this in Organic 1, so again, it's review. The tosylate is a good leaving group. Okay. Importantly, it allows for use of stronger anions. We'll see that and hopefully refer back to that. Tosylates are made from your alcohols, typically by reaction with tosyl chloride and a weak base such as pyridine. and this would be the corresponding tosylate. You got a propyl, oxygen. Now the oxygen is bonded to a sulfonyl. The tosylate comes from toluene. Okay. Benzene with a methyl is called toluene sulfonyl. And toluene sulfonyl has been shortened over the years to tosyl. Okay. And so we can abbreviate it as OTOS. All right. Now actually that's sort of me. The official abbreviation is OTS. But I always like to include the O in there so we can say OTOS. All right. And the tosylate is a good leaving group. It'll leave that carbon. And now we can get a strong nucleophile, the lone pair, and come in here, and these electrons can come in here and attack the carbon and kick off the tosylate. Nucleophile now bonded to the carbon. And the OTOS, of course, when that leaves, we have oxygen, SO2, and then there. The oxygen has two lone pairs here. Takes on a third lone pair, and that's a minus. Okay. But there you go. There's your OTOS anion, which you should know the full structure of. This would be an SN2 that I illustrated here, yeah? Okay. But let's look at the mechanism for forming the tosylate. Okay. Got our alcohol here, and we react with tosyl chloride. This is where we have a chlorine bonded to the tosyl. Instead of drawing out that ring, can I just do phenyl or Greek phi? That's generic for an aromatic ring, okay? So I don't have to draw that out every time. You need to know the structure, okay? This begins by these electrons. The alcohol, the hydroxyl group, acts as a nucleophile. See, this sulfur is electron poor. We've got a chlorine pooling, oxygen's pooling, electrons attack. Okay? But, very important here, and this is the first time we are going to do this. We'll do it many times this semester. We're not going to immediately kick off that chlorine, because when the nucleophile attacks, the weakest bond will break away from the atom. The weaker bond is one of the pi bonds to oxygen. Okay? Not the sigma bond to chlorine. So we break away that and we move those electrons to the electronegative oxygen. Oxygen bonded to sulfur. Double bond here. Bond to chlorine. Single bond to oxygen now. Electrons up. We have two lone pairs here, of course. Now we have three lone pairs on the oxygen, and that oxygen is now minus. And we also have that toluene ring, which I'll abbreviate. One lone pair left here, positive charge on the oxygen. We just did a nucleophilic addition to tosyl chloride. Now, the next step. The next step can actually vary. Some books will do it one way, some will do it another. And the problem we have here we have a choice. The reason we have a choice is, when do we take care of the proton? Because when we're done, the oxygen has lost the proton. Okay, here's what we're making. When do we remove the proton? And different people will tell you different times. All right. I would remove it now to be strictly correct. But most books will remove it later. I don't think I'm going to be concerned about when you do it. Okay? Let's do it later. And then we'll come back and say, well, what if we did it now? So let's don't worry about the proton yet. Let's go back up here. This mechanism has so many points in it that we'll make throughout the semester. We already made one up here. We just made a second. Now let's make a third. Anytime you can make a lone pair, I'm sorry, let me go back. Anytime you can make a pi bond using a lone pair and kick off a leaving group, that is an easy thing to do. It is a fast step. Let's use one of these lone pairs and let's move them back in here and let's kick off the chlorine now. Okay, 3 lone pairs here, and that's going to give, let's make that like that, oxygen. Okay. Now we got this double bond here, but now what did we do here? Lone pair moved in and made pi bond, kicked off a leaving group. Now we have double bond to oxygen there. Okay, 2 lone pairs, and we have the toluene ring. And this oxygen over here is positive. We kicked off the chlorine, it took on a 4th lone pair, it became minus. I drew that pi bond a little crooked. I'd probably draw it straight, but it's actually, let's don't think about it, but I just happened to draw it crooked. It doesn't mean anything. Now we're looking to get final product, which is there. We can even draw both oxygens up like that. Let's make sure they're coming from the sulfur. And then the toluene ring. Right? There's your product. To get there, we need to get rid of the H. Well, what can take the H? We can actually use the chloride to take the H. These electrons take H, these electrons stay behind, and we would produce HCl. Okay? But instead, typically when you do this reaction, you don't want to produce a strong acid because it can cause you problems. So you typically include a weak base, and traditionally you include pyridine. And pyridine is benzene with one of the carbons replaced with a nitrogen, and it's got a lone pair, of course. And that's pyridine, which we included, sometimes just abbreviated as like that. Instead, let's let it act as a base and take the H. And instead of making HCl, we make that and Cl minus just there, and that's just the end result. That's called pyridine hydrochloride. Basically, the pyridine has neutralized the HCl in this reaction flask, and we get this actually a salt. Okay. So we don't generate HCl. Now, we could have actually have taken the H here, and that would have given that there, yeah, plus pyridine hydrochloride. Not yet, it'd be just pyridine without the Cl minus yet. And here's your balanced, your negative and positive. Then we make that pi bond kick off the leaving group. Then we get that, and now the Cl minus can sit here. So both roads lead to the same products. We use a weak base, so HCl is not actually formed. And here we had a choice. When do we take care of the proton? Okay. Either way works. Most books are probably going to show taking care of the proton after this. In reality, they're both probably happening at the same time. I would probably argue that you want to take care of as soon as it becomes acidic. Okay, it's not acidic here. Alcohols are not acidic in the acidic, but this looks like H3O plus, a protonate, a positive oxygen, much more acidic. And if you got pyridine around, it's going to want to take it right now. But you can wait. Okay. It's a good mechanism for here on first lecture because it includes, we had 3 key statements. Please review them. By the way, that was nucleophilic addition. Right here we have the chlorine leaving, elimination. Elimination of leaving group. Okay. And overall, this is called an addition elimination mechanism. It is a substitution mechanism because the oxygen replaced the chlorine. All right. Instead of a chlorine bonded to the sulfur, we now have an oxygen. It is a substitution. The mechanism is not SN1, not SN2. It's actually a new substitution mechanism, okay, referred to as addition elimination. Nucleophilic addition followed by elimination. All right, this is your rate determining step. All right, anytime you can make a pi bond, kick off a leaving group, that's typically a fast step. So the elimination of the chloride is fast. All right, and the third statement is, when do we take care of the proton? Okay, there's your tosylate. There are variations of the tosylate. Mesylate, that's where instead of having a toluene ring, we have a methyl group. And it's called methyl sulfonylate, mesylate. If the H's of the methyl are replaced with 3 fluorines, it's called a trifluoromethylsulfonyl. That's shortened to triflate. And in all these, the nucleophile, a nucleophile can attack and kick off that oxygen. All right. By the way, why is this a good leaving group? Because the species that left, the oxygen that is left, is resonance stabilized a good bit. The charge is delocalized over 3 oxygens. Okay. Okay. One last thing here. We also have the dimethyl and diethyl sulfate. These are esters of sulfuric acid. If we replace those methyls with H's, that's sulfuric acid. All right? And this is diethyl sulfate. Now, if you cover this end up, that looks like a methyl and a tosylate. Instead of the toluene or the methyl, the CF3, it's another O-methyl. So it's actually symmetrical. But one side can serve as the electrophile kick that off. Typically, it only reacts on one side. Theoretically, it could react on both. Okay? But it's analogous to tosylate. Okay? By the way, you may not see these in your textbook. Okay? These are actually more common in upper level. Tosylate is covered at the introductory level. These are very cheap and thus very commonly encountered in the lab. You got to be careful though. These tend to be toxic. Okay? Anytime you have a great leaving group, your substrate can be fairly toxic. But these are almost like doubly activated because they can react on either side, and thus the rate of the reaction tends to be twice as fast as something with only one leaving group. All right. It'd be a methylating reagent, an ethylating reagent. These are all alkylators. Okay. But analogous to a tosylate. Okay, for homework. So we know what tosyl chloride pyridine would do. Okay. Now keep in mind, when we made the tosylate, okay, if this carbon was chiral, where the OH is, we would have no change. Okay? Whenever you make your tosylate, there's no chemistry done at the carbon that the OH is on. And so you would have no change in stereochemistry there. Okay? See, in this case, the carbon that the OH on is chiral. When you make your tosylate, no change in stereochemistry. But of course, when we do an SN2, we know SN2 comes with inversion, like Big Mac comes with fries. Okay. 2 for you to think about there. All right. I think I'll end this first video here. Some good stuff here in our mechanism. Got some homework there to work on. We'll pick up in the next video with C, actually still under substitution. It's actually another way to make alkyl halides other than using strong acid and halide. Some new reagents. Okay, guys. We'll end it there.